So this one's funny. Okay, we are live on the internet, and I need to share the desktop. And we have homework questions from 5.2, that's 5.1, 5.2, 9, and 19. Okay. So, playing around with sums. And that's not, I think we might need to dim the lights a little more. Okie dokie. So this is 5.2, number 9 online, and that's one in the book too, I can't remember which one. So for my version, it says the sum as k goes from 1 to n of a sub k is equal to 11. And the sum as k goes from 1 to n of b sub k is 12. And then they want me to mess around with some of the properties of sums. So for example, in 1a, or part A, I'm asked what would the sum of 8 times the AKs equal? And if you recall the distributive property of multiplication over addition, right, all this means is I have 8 times A1 plus 8 times A2 all the way down the line to 8 times the last A sub n. And if every number has the same factor, I can just pull that factor out, right? So I could rewrite this as 8 times all of those A's added up. Oh shit, how did that happen? All right, static electricity, I'm gonna blame it on. So the general rule for something like this is if you have a constant multiple of something that's being added, you can pull that multiple out. So it's just 8 times whatever the sum of the A's is. The sum of the A's is 11. 8 times 11 would just be 88. Okay, so it doesn't matter that whether we know what the individual A's are. All that matters is if we multiply a number by a sum, we can either do it term by term or undistributed. Okay. All right, so part B says what would happen if you took the sum of the B's and, oops, I'm ahead of myself there, and my tools disappeared. I hate that. Where'd you go, tools? Come on. There you are. What if we divided each b sub k by 12 on the inside? Well, division's no different than multiplication. I could say this is really just the sum of 1/12 of each b sub k, and I can pull that 1/12 out. Oops, b sub k. The b's added up to 12 is my recollection. Yep. So then this must be 1/12 times 12 or 1. So this is just properties of sums. Okay, so some other properties of sums that we have are if you take the sum of a bunch of A's and a bunch of B's together, you can always break that up as the sum of the A's plus the sum of the B's. And subtraction's really no different than addition. If that was a minus there, that would be a minus there. Well, it depends on whether it was the plus or the minus, right? So in part C, they said do the plus version, AK plus the BKs. And I can just reorder those, right? Because when I write that out, that's going to be A1 plus B1 plus A2 plus B2, all the way down to AN plus BN. And can't we add any order we want? Yeah, so we can take and do all the A's first and all the B's second, which is what this says right here. So that must be 11, right? Is that what the A's were? Yeah, plus 12 the sum of those guys, then the sum of those guys. So the answer there would have to be 23. If there was a minus in between, then it would have to be 11 minus 12, which should be -1. Okay. Then they gave one more that was a bit more complicated. They said, well, what would happen if you took the sum of the A's plus 3 times the B's? Well, that's multiple rules happening at once. We have the sum rule that says you can just separate out the A's from the other side of the sum. And then we have another rule that says if you have a constant multiple of every single term, you can pull that, factor it out of the sum. So that would just be the sum of the AK's plus 3 times the sum of the BK's. All right, so that just allows me to dissect a sum and do it in pieces, which is going to be super useful for some of the problems we'll do in a minute. So that would have to be 11 plus 3 times 12, which is what, 36 plus 11 is 47 on a good day. Okay, so just getting used to those sums, those sum properties. Oh, sorry. My daughter is homesick and thinks she needs to talk to me again. And I don't know how to turn off the volume. Do I just do that? Do I do that? There we go. She's silenced. Okay, 19. What was the next question? Oh, 19's a great one. We'll get to use these rules of sums. All right. So number 19 in 5.2 was you were given a function f of x equals something like, and yours had slightly different numbers, but it was close to this one, 5x plus 5x squared. And we were to look on the interval from 0 to 1. And we were to create a sum for the area under the curve. And we were asked to do right-hand endpoints. Now, I've used the word Riemann sum in some of the videos I've done. I'll talk more about what a Riemann sum is. It's not much different than, say, a right-hand sum. So we want right endpoints. And we are told here to also make n intervals, or n subintervals. So instead of saying break it into 4 intervals or 10 intervals, they're saying just make it n. Could be 4, could be 5, could be 2, could be 100, right? We just have n. So the procedure for doing this is always pretty similar. First step is if you're doing the same width interval, you figure out what the width is. So I usually call that delta x. And that would be how wide is my interval? So in this case, 1 minus 0 is 1, divided by how many pieces I want that interval to contain. And I want it to have n pieces. Okay. So now I'm taking the number line from 0 to 1, and I'm breaking it into chunks. And each of those chunks we've just determined is 1 over n wide. Okay. And the procedure is always the same there. It's always the right endpoint minus the left, right? That gives you the width of the starting interval, and divide by how many pieces you want. So we want n pieces. Okay, sometimes the question said do 4 pieces, right? That's relatively easy to draw and do. Once we get higher than 4, it's just a pain in the butt to do by hand. Okay. The next trick is then to decide, okay, I have some curve floating through here, right? So let's just have this fictitious curve floating through. I'm going to be making these rectangles. I have to decide how high the rectangle is going to be. Okay. Well, the function determines the height. So then we have to say, okay, we could do right-hand endpoints, in which case my rectangle would be that high. If I did a left-hand endpoint, right, that would be left-hand endpoints. Sometimes we choose to do something like the midpoint of the interval. But technically, you can pick any point inside the interval, any point you want. Okay? It's easiest to just say, hey, let's just go with one side, the other, or the middle, because then those numbers are predictable and have a formula. Do you remember reading in the book, they talked about upper sums and lower sums? Okay, upper sums and lower sums are a total pain in the butt because sometimes a right-hand endpoint will be a lower sum because it's underneath, but other times the right-hand endpoint is an upper sum depending on whether the curve is increasing or decreasing. Okay, so in my opinion, I like to avoid upper sums and lower sums because they're unpredictable, because I have to evaluate each interval and decide, am I going on the right or the left or in the middle somewhere? Okay, so usually when we're asked to actually calculate a sum, either we'll be told to do a right, a left, a mid, or sometimes what's called a trapezoid. Okay, and right generally is the easiest one to do. All right, so from here, to generate right-hand endpoints, the procedure is always, again, the same. You say, okay, where am I starting? And usually we call A the starting point. In this case, my A is 0. And then from there, we just keep adding 1 over n's, right? Add a 1 over n, add another 1 over n, add another 1 over n. So what we're going to do is we're going to add multiples of 1 over n. Now, if A is 1 or 2 or 3, then you've got kind of a complicated linear expression to deal with there. But here we're lucky because A is 0, right? So we have 0 plus multiples of n. So summarizing on the next page, we have f of x equals 5x minus 5x squared on the interval from 0 to 1. We've decided to do n subintervals. So that means the width of each interval is going to be 1 over n. And each x value that I'm going to evaluate at, I call that as the xi's, they're just going to be some multiple I of 1 over n, which cleans up to be just I over n. So this is the number I will evaluate f at to get the height of each rectangle. Okay. So agreed, I'm going to have a whole bunch of rectangles, right? Each rectangle is going to have a width we call delta x, right? Delta just means a small chunk of the x-axis. So what we're generating are small chunks of area. Each area has to have a base and a height. What's the base of each rectangle here? The width of each base. It's just 1 over n, yep, so that's base. And the height, we have to ask the function what's the height. So the height always comes from the function value. So in this case, our function says take 5 times some x value minus 5 times some x value squared. What x values are we plugging in to get our height? The x sub i's, which is an I over n. So that goes inside here. So that's I over n, I over n. So that's what each individual rectangle's area looks like. Now we have to add those suckers up. All right, so here I goes from 1 to n. Has anyone joined online? Nope. And these are the things we're adding. 1 over n times 5 parentheses, then another parentheses, I over n. And I always put extra parentheses at first to be safe. We can clean them up later. I over n squared, close. You might notice the book writes them slightly different than I do. They usually write the 1 over n at the end, but I always think of area as base times height, so I write it first. Does it matter what order you multiply in? No, do it any way you want. Yeah, so here's the other thing, right? The variable of the sum is the I. There's a variable, there's a variable, there's a variable. Now, you might say n's a variable, but it's really not. Because when we actually do this, we have to say, okay, we have 4 intervals or we have 10 intervals. We have to ultimately pick an n. So n is really a constant in this scenario at the moment. Okay. Cool thing about constant multiples is they can be pulled out of the thing. Okay, and we can do that now or later. So now we have to do some algebra on this sucker to figure out if we can clean up the sum, because we do have some tricks for cleaning up sums that we generated last class. So I can either decide to pull out that 1 over n now, or I could say, well, I might be okay to distribute it through. And you never know what the easiest way is till you've done them both. Now I've done them both and I don't want to spoil the surprise. What should we do? Should we multiply it through or pull it out? Distribute. Okay, good. That was my gut instinct too, right? All right, so we're going to distribute that through here. So we need a new page. Okay, so we've got our sum. Oops, that's a highlighter. Pen. We have our sum as I goes from 1 to n, and we're distributing that through. So that's going to give us, let's see, back here. Well, I could view that as a 5 over 1, right? So I could maybe throw all that stuff together right here. So that would give me 5i over n squared for that first chunk. Correct me if I screw anything up. So I think I'm going to have a 5i over n squared minus, well, this is going to be an I squared over an n squared way on the right. 5 goes into the top, another n goes into the bottom. So I think that looks like what, 5i squared over n cubed? I think 5i squared over n cubed. How's my algebra? Doing all right? Stanton's not arguing, so I think we're all right. Clint, you all right? All right. Jesus, good. All right. Sam, okay. It's a cool hat, by the way. All right. We have a rule that says we can break a sum on a difference. So I can break this into parts. This would be the sum. I goes from 1 to n of 5i over n squared minus the sum as I goes from 1 to n of 5i squared over n cubed. Now I can think about these guys individually. So I can just do the one on the left first. Are there any constants I can pull out of the one on the left? The 5 and? Yeah, the n squared is a constant because it's the I that's changing in my sum. So n squared is really constant in this particular moment. So I can pull out the 5 over n squared, and I can just say, oh, can I do anything with the sum of the i's? Do we know a shortcut formula for the sum of a bunch of whole numbers? 1, 2, 3, 4, 5, on and on? Oh, you guys don't remember? I was so excited about this in class on Tuesday. Yeah, it turns out we do have a formula. I can't remember what page in the book it's on. Let's take a sneak peek at the book. It was way back, I think in section, yeah, it's in this section right here. Where'd you go? Oops, I went too far. Right there. Oh, whoa, stop. What are you doing? My mouse is freaking out. Okay. Blow that sucker up. Whoa, that was big. It says if you add up a bunch of integers starting at 1, ending at n, the sum will always be n times n plus 1 over 2. I proved that one in class. I didn't prove the squares or the cubes, but we have formulas for those too. Okay, so it turns out we can clean the rest of this up. So what we just saw on the screen there was a formula for that right there, and it is always n times n plus 1 over 2. We have that constant multiple outside, 5 over n squared, minus this one right here. What's constant in the second sum? The 5 again, right? And the n cubed is also a constant. So I've got 5 over n cubed. Ooh, whoa, that got crazy. Happens when I get excited. I goes from 1 to n of I squareds. And it turns out the book did give us a formula for the sum of the I squareds. And after you see it a few times, you kind of get used to it. It's similar to the first one. It is, so this guy right here, n times n plus 1 times 2n plus 1 all over 6 would be the sum of the n, the squares of the first n whole numbers, or counting numbers. And we have that multiple of 5 over n cubed hanging out front. And we could do a little more algebra and clean this up more, but I'm going to stop with the algebra there. What this tells me is, notice the sums are gone. I don't have to add anything up anymore. All I have to do is multiply, divide, and subtract. So you tell me how many rectangles you want, 5, 10, 100. I just plug in 5, 10, or 100 for n, and bang, I have the right-hand sum for the area under the starting curve, is what this formula gives me. Now, thinking back to calculus 1 for a minute, you found, remember the whole difference quotient, the f of x plus h minus f of x all over h, and you took the limit as h went to 0? Now here, our areas will get better and better as we break the interval into more and more pieces. So what we really want to see is what happens to this resulting sum answer as we let n get bigger and bigger. Does this have a limiting value? Or does it keep growing forever? Well, let's take a look at the graph of this function to get a peek of that before we continue with this exploration. Our function is 5x minus 5x squared. Squared. Uh-oh, I broke GeoGebra. Come on, you can do it. Interesting. Come on, show me a graph. I don't really want to graph this by hand, but I will if I have to. Oh, there we go. 5x to the second. There it is. And we're going from 0 to 1. So looking at this right here, we can see, yeah, there's definitely some area there. And GeoGebra is kind of fun because if I grab that move tool here, I can then grab hold of the axis and rescale it and reposition it. So I find it a little easier to use than Desmos once you get used to some of the tools you have available, right? So what we found is, for example, interesting, why are you freaking out on me there? Go away. If I do a rectangle sum, this particular function called f from 0 to 1 with, let's say, 4 subintervals, and we are doing right-hand endpoints, which is a 1, that would be what 4 looks like. So if we plug 4 into our crazy work here, we will get the same area that Desmos just told us, which it didn't draw the area on the screen. Usually it does that. Oh, I didn't hit enter yet. There it is. We'll get 0.78125. And would you agree if I keep upping the number of rectangles, I'll get a better and better approximation? Like if I jump up to 10 or 100, I'll get closer and closer to the true value of the area under there. And we talked about this in class the other day. We have formulas for the areas of triangles, trapezoids, rectangles, circles, but there aren't standard formulas in most geometry books for the areas under a parabola or a cubic or some other kind of function that we come across in a class like this. Right. So, limit is our next stage. I need a magic pen. Here it is. Okay, so help me get this right on the next screen. We want to take the limit as n gets bigger and bigger and bigger. And I think we have what? There's a 5 in the numerator, there's an n plus 1. In the denominator of the first part, I think it's just a 2n squared if we throw all that together in the first part. And then over here, we have, let's see, there's another 5, an n plus 1, a 2n plus 1, and in the bottom, we should have a 6n cubed. Did I get all that right? Okay. All right, well, these are just rational functions. And back in the beginning of Calc 1, you learned about limits of rational functions. And the rule was if the degree of the numerator was the same as the degree of the denominator, then the leading coefficients dictate the limit of the rational function. That sound about right? Let's see. All right, so focusing on this fraction, does this rational function and that rational function have the same degree? Yeah, they're both degree 2, right? So that means the limit of this particular fraction should be 5/2. Does the next fraction have a finite limit? Yeah, they're the same degree, right? They're both cubics. Leading coefficients are 5/6. We've got a limit. We can clean up that a little bit. We need a common denominator. So I'll multiply this by 3. 15 minus 5 is what? 10/6, which reduces down to what? 5/3. 3 goes in there 1 2/3 times. Or 1, if we rounded to the nearest hundredth, 1.67-ish is about the area under this particular curve, we think. Okay, because what we just did is we said, hey, let's have infinitely many rectangles, right? So let's see, is that what the sums in GeoGebra were leading to? So one thing that's nice, ooh, no, they're not. Interesting. Do we have a mistake somewhere? GeoGebra said it should be about half of that. Ooh. Fascinating. Okay. We must have an error. Either that or I typed the wrong function into GeoGebra. We went wrong somewhere. What do you think? 5x minus 5x cubed. That's what we started with, true? 5x squared, excuse me, yeah. That's what I have here. Oh shit. Okay. Let me blow this up. Let's see. Font size 24. It's a little better. Okay, what did I start with? Where's my notes? There I have a minus. Minus, minus. Okay, I have minuses. Okay. One more? Oh. Yeah. Oh, interesting. Okay, so we started with a plus there, and somehow I switched to a minus here. But I was consistent with my minus all along. Right? I still have my minus everywhere. And in GeoGebra, where'd you go, GeoGebra? I stuck with the minus, and I still have half. Okay, so although I switched problems from the beginning, I'm consistent in GeoGebra and my notes. But there's still a disagreement. GeoGebra said it should be 0.8-ish, we got 1.6-ish, so our answer is twice what GeoGebra says it should be. Why? Did I miss a factor somewhere? Why are we twice? I do not see it. Okay, we're going to have to come back to that later then. Did I mess up on one of these here? No, those are both right. That's possible. N plus 1, 2n plus 1 over 6. Oh, shit, yep. I see there. Yeah, right here. I forgot about that 2. If you multiply all of this out, your leading coefficient will be 10 n cubed. Right, 5 times 2 is 10. What do I have written here? A 5. It should be 10. That's the mistake. You just saw that too? Okay, good job. All right. Yeah, so doing this in class is like taking a test, pressure. So if this happens to you on a test and things aren't matching, best thing to do, get a blank piece of paper and start again, because you're likely not to see your error. All right, so where are my tools? There they are. Okay, so the error is right here. I forgot to incorporate that 2. 2 times 5, this should be a 10 right here. So if we make that a 10, then we have 15 minus 10, which is 5/6. And 5/6 is 0.833333333. Yeah. And now we match GeoGebra. Whew. Isn't it nice we have that technology to check stuff out? It's pretty cool. When I was taking calculus, we didn't have that, unfortunately. And so the only thing I could do was do it by hand with 4, push it, try 5, hope my numbers were relatively close to what the limit said, because technology wasn't sufficiently advanced enough to do that. Although spreadsheets were just coming out. You can do all this stuff on spreadsheets too. That automates things nice. Okay, that was exciting. All right, so we are going to, that was number 19, sort of. I changed the addition to a subtraction, but it's the same idea. All right. Next, let's see, I had some ideas in my notes. Let me bring up my notes. Let's see, where did I post my notes? Not here, I think it was on the intro page. Not the calendar. My notes, okay. So when I have free time, I like to type pretty math. I find it soothing. Kind of like yoga or biking up a steep hill. All right, so let's see, this is 5.2. We've gone over most of this stuff here. I think I do want to do a cubic with left-hand sums like this one. All right, and then, so we'll do that in a sec. Let's see, do I have recent posts? Okay, 5.3. Open a new tab. Okay, and you talk about partitions and definition of a Riemann sum. Okay, so we're going to do this boring stuff, definition of a Riemann sum, and then we'll go do some more exciting problems like the one we just did. All right. Pen's disappeared again. Someday I'll fix that problem. So a Riemann sum is just kind of a generalization of the idea of a sum based on a function with a boundary, right? So we have some function f of x as a boundary curve, boundary. And usually we have starting points A and B, and it doesn't have to be interpreted this way, but the most popular interpretation is we're looking at the area under a curve. So that's why I'm calling it a boundary curve. We have this strange curved top, but we have nice straight sides and a straight bottom. And the next step is choosing to partition the interval. And the idea of a Riemann sum is it could be absolutely any partition. Okay, any possible partition. So we were making our partitions so that they were always the same width for the subintervals, but it doesn't have to be that way. Why not? Well, here's an example of why not. Suppose we had a function that looked like that, and A was over here and B was over there. if I make the partition all the same width, and let me just make a copy of this so we can try a couple things. This is kind of fun. I can shrink it. All right. If I make a fixed width partition here, like suppose I cut the partition, or I cut the original interval into quarters, then all my rectangles are going to be the same width, like that. And let's suppose we go with right-hand sums here. So they're going to look like this. Okay. Do you notice that as I move along here with the rectangles, and let's see, I kind of missed on that one right there. Oh well. When the curve is steeper, I get a lot of extra space I don't want. And when the curve is shallower, I don't get much extra space at all. Okay. So wouldn't it make more sense to be able to not worry about a fixed width, but to say, hey, where it's steeper, I just want thinner rectangles so I don't waste as much area when I'm calculating them. And when it's wider, man, I can make those as, pretty darn wide because I'm not wasting much extra area there. Or if we had a lower sum, right, happens to be an upper sum, but if we're a lower sum, I'd be losing area. Okay, so Riemann was a guy who was looking at this calculus and he saw all these people making these fixed width sums. He's like, well, they don't have to be fixed width, right? This allows me to get a better estimate. Now, the problem with this is you then have to deal with the fact that all of these widths are different and you have to pick a number inside to evaluate the height at. So it gets making the sum more complicated, but it preserves the area better. Okay, so that's the idea of a Riemann sum. So it just generalizes the sums we've been doing. The partition, we usually call it capital P. And then in the book, you'll see double bars around the P. And they call that the norm of the partition. And all the norm of the partition is the biggest width in the partition. Okay. So for the partition I started drawing over here, the first one, they're all the same width. So the norm of that partition would just be B minus A over N, or N was 4 in that case, excuse me. In this case over here, I've got a bunch of little thin partitions there, and then I got this big fat guy right there. So that, whatever that width is, that would be the norm of this partition. The biggest partition in the biggest subinterval in the particular scheme I've drawn. Okay. So what he then said after that was, if you then add up all of those, so you're going to have each, instead of calling it delta x, we're going to call it delta x sub I, because each place is going to be a slightly different width. And then you're going to evaluate the function at some number c sub I inside the interval. Okay. And what he said is, so you don't worry about your partition. It could be absolutely anything. It could be even or not. What you do is then you let the norm of all possible partitions go to 0. So you just keep, basically you're going to have to add more and more subintervals. Sometimes they're little, sometimes they're big. And this is what leads to the idea of what's called the definite integral. So the idea of a Riemann sum with this limit here leads to what's called the definite integral. And for some functions, it works out kind of nice. Like we played with some square functions. We're going to do a cubic function, and they work great. No problem. I can just choose to use right-hand sums. That's okay. There's some of the possibilities that exist over here. And I can take the limit of those right-hand sums, and that leads to the idea of what's called a definite integral. Okay. The problem is there are some very simple functions for which neither a right-hand sum nor a left-hand sum nor a centered midpoint sum lead to anything we can clean up. Okay. So a simple example of one that we really can't clean up, consider the function 1 over x on the interval from 1 to 2. It has 0.11, it has a 0.212, and a 0.112. If you remember this function from previous classes, it has a horizontal asymptote that is the x-axis and a vertical asymptote that is the y-axis. And I really can't start my interval at 0, because what happens if I try to plug 0 into this function, like for a left-hand endpoint? Error, yeah, it's like it's infinitely high. That's a problem. Right, so that's one reason I'm starting at 1. So I don't worry about this crazy infinity stuff going on right there. And then I'm just going to go over to 2, say. Easy partition would be the width of the interval is 1, split it into n chunks. Okay, so that would be my delta x. And then my x sub i's would just be starting at 1, add I multiples of 1 over n. And when we throw that all together, so this is the number I get to plug into my function to get the height of each rectangle. My sum looks like this. The sum as I goes from 1 to n of the width, 1 over n, times the function 1 over this x value, 1 plus I over n. And then I have a couple of choices. I could pull out that 1 over n, or I could multiply it through. And I'm going to do what Stanton did before. I'm going to multiply it through the fraction here, because things clean up nice when I do that. So new color. This is then equal to the sum as I goes from 1 to n of 1 over, well, I have to distribute this n through here. 1 times n is n. What's n times I over n? Plus I. That's kind of nice and clean, ain't it? Downside. Although we have a shortcut formula for adding up 1, 2, 3, 4, 5, 6, or 1 squared, 2 squared, 3 squared, 4 squared, there is no shortcut formula for that sucker right there. Which means when someone tells us to take the limit of that as n gets big, there's nothing we can do with it. So what that means is somebody has to find a more clever partition to make that able to break down the limit. My recollection is in my past life, I've seen a clever partition of that, but over the last 2 days of screwing around with it, I couldn't come up with it. And I haven't searched the internet for it yet. I'm going to continue to beat my head against the wall for a few more days. So sometimes we can get these relatively simple functions, and all of a sudden, bam, we just hit this brick wall. And some of these brick walls people have hit in the past, it took like 100 years or more for somebody to come up with, you can do it or you can't do it. Sometimes you can and sometimes you can't, you just never know. What does that mean? Does that make this definition useless? No, this is the definition of the definite integral. Okay, what we need is more tricks. And you learned one of those tricks last term. What was the last thing you did in calculus last term? Antiderivatives, maybe? Looking at derivatives backwards. Yeah, it turns out there's a connection between derivatives and antiderivatives, and antiderivatives are related to definite integrals. So everything you learned about derivatives, we can then use to try and come up with some of these integrals, aka antiderivatives. So although sometimes the Riemann sum will throw us for a loop, we're stuck, we're going to generate other tricks to help us figure it out. Like, remember, didn't it take a while to get certain derivative rules in calculus? Right? You got the power rule right away, and but then you had to learn, what was that? The chain rule. Didn't that just, that hurt, didn't it? The chain rule hurt a little bit. And then you had to do derivatives of trig functions. They weren't obvious. And then derivatives of inverse trig functions, right? That was tough stuff. So it's the same thing with integral. And integrals are actually harder because we're doing derivatives backwards. And it's usually harder to do things in reverse. Like think about multiplication. That's not that bad, is it? But how many people love long division? Besides Stanton, right? So usually when you try to do something backwards, it's harder. We're just about out of time here. I promised that I would do a cubic, and I ran out of time for the cubic, so we'll do that next class. So where are we now? We are slightly behind schedule, and that's okay. I expected that to happen. So let's see, where's my calendar? Next page here. Okay, so I was hoping that we would finish 5.3 today, but we're not. We're about halfway through 5.3. 5.3 actually isn't that bad. That definition looks crazy and scary, but it's not that bad. There are some tricks I need to show you about the definite integral that are similar to the tricks we did at the beginning of the class, manipulating sums, because it turns out an integral really is a fancy sum. So anything you can do with a sum, you can do with an integral. So what I'd recommend is take a read through 5.3 as soon as you can. And then we will pick up trying to finish up 5.3. 5.4 is where we make the connection between antiderivatives and integrals so that we have more tricks up our sleeve to try and evaluate these things when the Riemann sum makes us stuck. Now here's the other thing. That Riemann sum we did for the parabola, was that easy or hard? I found it wicked hard, and I made a mistake, right? It wasn't trivial. That was a lot of algebra to push through that. We don't want to have to do that every time. So we're going to generate shortcut rules like you had shortcut derivative rules, okay? And so once we get 4 under our belt, then the rest of the quarter is like pretty much generating shortcut rules. So the theme of this class is pretty similar to the theme of Calc 1. First, you play around with that limit of the difference quotient, and then you start getting all these shortcut rules, and then you start doing really hard functions, and then you start applying it. Same thing here. We're about to start building shortcut rules based on the theory, and then after about a month of that, then we start applying it to interesting physical problems. So will the exam still be on the 26th? Maybe. Maybe it's going to be on the 30th. We'll see how we proceed here. But right now, we're only partially through 5.3. With that in mind, you might not finish the homework by the deadline I set. I think I set that deadline to, is it tonight? 5.2 should be tonight. Yeah, I think 5.3 is like Monday or Tuesday. You think it might be Saturday? Oh, good. So the due dates are there to push you to get work done. Because to be successful in a class like this, I'm sure you've already learned this, you got to do a little bit of math every day. Otherwise, things pile up and you get hurt. If you happen to not be able to keep up with the schedule I set for the homework, I usually put a little safety in there. And here, there's a password to get you back in should you not get it done in time. The password is, anybody want it? Yes? Okay. Password is get it done. All one phrase. No caps, no spaces. Okay, so if you shouldn't finish all of the homework, please try to get it done by the due date. Otherwise, things are going to, accumulate in a bad way. You get that to get you back into it. Okay, and I usually keep that open like that until the test day, and then I shut it off completely. If people start abusing that by like putting it off and off and off, then I will pick on people individually, but not the class. So hopefully everyone's doing pretty good so far, keeping up with the homework. All right, that's it. Have a good day. Do good math. Be careful out there on those crazy roads. Oh, and then the other thing is every Friday, I'm leaving 11 o'clock as a time for question and answer for calculus. So if you happen to be free then, come up. Anybody that does come up, I will record any questions we do together and post that on YouTube too. At 11 o'clock, yeah. So if you're bored tomorrow,